so today is the fifth in an 8-part climate science series, co-hosted by Katie Reeves of the U.S. Global Change Research Program and myself, Tracy Gill from NOAA. I'm going to provide a few logistics about today's seminar, and then Katie will introduce the seminar and the speaker. We have switched to Adobe Connect for this seminar series to accommodate more participants and to record the seminar. The recording and a PDF of today's presentation will be available after the webinar, and we will post a link to the recordings in the chat box. So for today's seminar, you can ask questions in the chat box, and the presenter will address them when he has a chance. People in the room, please sign in and silence your phones. And now Katie is going to introduce our seminar and the presenter. Katie?
Thanks, Tracy. Good afternoon, everyone. Thank you for joining us for the Climate Science Special Report webinar series, Part 5. My name is Katie Reeves, and I'm the Engagement and Communications Lead for the U.S. Global Change Research Program, or USGCRP. To just give you a brief background, the Global Change Research Act of 1990 mandates that USGCRP assist the nation and the world to understand, assess, predict, and respond to human-induced and natural processes of global change. One way that we do that is through the development of a quadrennial national climate assessment. The Climate Science Special Report, which is the focus of this 8-part series, represents Volume 1 of the 4th National Climate Assessment. The report assesses the science of climate change with a focus on the United States and serves as the foundation for Volume 2 of the assessment, scheduled for release late this year, which will look at climate-related impacts, risks, and adaptation across the U.S. The Climate Science Special Report was released in November 2017, and you can read and download it at science2017.globalchange.gov, and I've also already put that in the chat box. Today, I'm pleased to introduce a good friend of USGCRP, Ben DeAngelo, and his presentation, Long-Term Climate Mitigation Perspectives and the 2 degrees Celsius Objective. Ben has over 20 years of experience bridging science and policy for the stewardship of the global environment. He's the Deputy Director of the Climate Program Office within NOAA's research arm, where he has been since 2017, and he serves as the U.S. Head of Delegation for the Arctic Monitoring and Assessment Program, a working group under the Arctic Council. I had the pleasure of working with Ben during his days as Deputy Director of USGCRP and Special Assistant for Climate Change to the President's Science Advisor. Prior to joining NOAA, Ben had an 18-year career at the EPA working on climate change and stratospheric ozone depletion. And as you'll learn today, Ben was the lead author on the Mitigation chapter of the Climate Science Special Report, on which this presentation is largely based. So thank you so much for joining us for today's NOAA Science Seminar. Ben, take it away.
Great, thank you, Katie. Thank you very much for that intro, and thank you, Tracy. Thanks to the people here in the room who have joined, and thanks to all of you who are joining online. I really appreciate the opportunity to talk to you about the issues and statements in our chapter. So as Katie said, this presentation, Long-Term Climate Mitigation Perspectives and the 2 degrees Celsius Objective, is based primarily on Chapter 14 of the Mitigation chapter of the Climate Science Special Report, or CSSR. And as you heard from Katie and perhaps other speakers in this series, CSSR, published last year, serves as Volume 1 of the 4th National Climate Assessment. So this report, CSSR, provides the consistent scientific underpinning for the remainder and Volume 2 of NCA4, which focuses more on societal effects and risks for different regions and sectors of the United States. And as Katie said, that Volume 2 of NCA4 is in the final stages of development. Also, the National Climate Assessment itself is a congressionally mandated product under the 1990 Global Change Research Act. And CSSR, this report, fulfills certain elements of that mandate in that it discusses remaining uncertainties in climate science and provides future projections out over the next 25 to 100 years. So I just want to quickly acknowledge the co-authors on this chapter 14. They're David Fahey from NOAA. He's the director of the Chemical Sciences Division in the NOAA lab in Boulder. Benjamin Sanderson from the National Center for Atmospheric Research, Jay Edmonds from PNNL, Pacific Northwest National Laboratory, and also Catherine Hayhoe and Michael Weiner, who are also lead authors on CSSR, provided really good and valuable contributions to this chapter as well. Why a chapter on mitigation issues in an assessment focused on climate science? So we wanted to provide scientific information relevant to mitigation questions in the policy arena, but without being policy prescriptive. We stay in our science lane, and you won't find any policy or implementation recommendations in this chapter or in the entire report. So let me give you an overview about what I'm going to talk about. I'm basically going to cover these four topics, and in fact, I'll be providing the four major findings from our chapter with a lot of supporting information. So these are important concepts for any mitigation trajectory, such as the long-term nature of the CO2 climate effect and the short-term nature of some of the non-CO2 species. Carbon budgets. This is about basically how much can we emit into the global atmosphere if the goal is to present X amount of warming, 1.5, 2C, etc. And then the 2C, the 2 degrees Celsius objective itself, there's obviously a lot of attention to that. I want to provide a little bit of history on that and also show some analysis we did addressing the question about whether we are on a path to achieve that. And then finally, a topic that is admittedly very controversial are the geoengineering questions and concerns. So we do have a section in our chapter that addresses that topic. So the first finding in our chapter, let's keep finding one. Let me actually just read it for you. Reducing net CO2 emissions, net emissions of CO2 is necessary to limit long-term warming. Other greenhouse gases, for example, methane and black carbon aerosols, exert stronger warming effects than CO2 on a per ton basis, but they do not persist as long in the atmosphere. Therefore, mitigation of non-CO2 species contributes substantially to near-term cooling benefits, but cannot be relied upon for ultimate stabilization goals. So in the next couple of slides, I'll unpack this a bit and show some supporting evidence for these statements. I just need, there we go. So, long-term warming. The long-term human-induced warming influence on the globe is dominated by cumulative CO2 emissions, and the key word there is cumulative. CO2 is unique among greenhouse gases. It's long-lived, like many other greenhouse gases, in the atmosphere, but different portions of a pulse of CO2 emissions that get emitted into the atmosphere get removed from the atmosphere at different rates. So initially, after you have a pulse of emissions in the atmosphere, there's initially a rapid decline of that CO2 from the atmosphere over the first few decades. But then that kind of removal from the atmosphere slows, and then is followed by a long drawn-out tail, actually by a millennium scale tail, where it takes thousands of years for the final fraction of a pulse of CO2 emissions to be removed from the atmosphere. So this is why IPCC estimated that 15 to 40%. of CO2 emitted until 2100 will remain in the atmosphere longer than 1,000 years. And on top of that, the persistence of warming is longer than the atmospheric lifetime of CO2 and other greenhouse gases, owing in large part to the thermal inertia of the ocean. So this means climate change resulting from anthropogenic CO2 emissions is essentially irreversible on human timescales. And therefore, it also means the world is committed to some degree of irreversible warming and associated climate change resulting from the CO2 emissions that we've already put into the atmosphere. And getting to the topic of informing mitigation, the long lifetime in the atmosphere of CO2 and other gases, again coupled with the long time lag in the response, the warming response from the atmosphere, has timing implications for the benefits of mitigation actions. And here, when I say benefits of mitigation actions, I mean essentially the avoided warming or avoided risk as a result of mitigation actions. And some of those kind of implications include, first, that a large reduction in emissions of the long-lived greenhouse gases, including CO2, are estimated to have a modest temperature effect in the near term. I'm talking over the next couple of decades or so. And then secondly, over the longer term, long-term projections of global surface temperature, here I'm talking after mid-century, show that the choice of global emissions pathway, and thus the long-term mitigation pathway the world chooses, is the dominant source of future uncertainty in climate outcomes, especially at large scales. And let me just show this graphic that further illustrates this last point in particular. So what it's showing is the fraction of total uncertainty or variance in temperature projections over time, explained by three buckets of total uncertainty. And this is shown for the lower 48 states. So orange represents kind of human choice or scenario uncertainty, and you see that over time it becomes the dominant source of future uncertainty. Blue represents model uncertainty, and green represents internal or natural variability. So if the size of this region were smaller, say a smaller region of the United States or a state, the relative importance of the green part, the natural variability, would start large but remain much larger over time. And then the other point here is that it's important to remember that this is showing relative sources, fractions of uncertainty, but of course total uncertainty does increase as time progresses. So of course a temperature projection for the year 2100 is going to be less certain than global temperature projections over the next 10 to 20 years. Okay. So now I want to talk more about the non-CO2 species that I mentioned in that first chapter finding. So this bar chart, also from the report, this bar chart shows the influence of anthropogenic factors, namely through emissions of CO2 and non-CO2, and natural factors in the form of changes in solar output. Volcanic forcing is always a cooling effect, but it's not shown here because it's very episodic in nature. The metric here is radiative forcing. That's basically a change in the energy balance of the Earth. Radiative forcing exerted on the global climate from pre-industrial times to close to the present day. So the bars to the right are positive forcings or warming effects, and the bars to the left are negative forcings or cooling effects. So you see at the top is the warming effect from anthropogenic CO2, and not surprisingly, it is the dominant anthropogenic influence on the climate since pre-industrial times. But you also see large positive forcings from other non-CO2 species as well. And here I'm talking about that second red bar, the other WMGHG. WM stands for well mixed, meaning those greenhouse gases stay in the atmosphere long enough, at least a year, to get well mixed throughout the global atmosphere. The second most important greenhouse gas directly emitted by human activities is methane. That's in that second red bar. The halocarbons in there also exert strong warming effects. These include the different generations of ozone depleting substances controlled by the Montreal Protocol. And I also want to point out the warming influence of black carbon aerosol. So black carbon, think of the sooty emissions, sooty, blackish smoke you see coming out of an old diesel truck or bus. That's black carbon. That's the only aerosol that has such a strong warming effect. It directly absorbs incoming sunlight. It also has a warming effect by darkening the surface of snow and ice surfaces, and that particular warming effect is explicitly shown in this graphic. But aerosols in total have a net cooling effect because most other aerosols reflect sunlight, and they also affect the albedo or reflectivity of clouds. So those are those negative bars to the left. So the point here for mitigation is that the mitigation of non-CO2 greenhouse gases with relatively short atmospheric lifetimes, such as methane, some of the halocarbons or HFCs in ozone, and then black carbon, and these have been collectively referred to as the short-lived climate pollutants. Mitigation of these substances has been highlighted as a particular way to achieve more rapid climate benefits. So these short-lived climate pollutants are substances that not only have an atmospheric lifetime shorter than CO2, but they also exert a stronger radiative forcing and hence temperature effect compared to CO2 on a per ton basis. Methane has an atmospheric lifetime of about a decade, and black carbon has a lifetime of days to weeks. So for these reasons, when you mitigate these kind of emissions, it produces a more rapid climate response. In the case of black carbon, because it has an atmospheric lifetime of days to weeks, it does not get kind of homogeneously distributed throughout the globe, and therefore emissions of black carbon aerosols and the flip side, mitigation of black carbon emissions produces strong regional effects. And then again, if you're informing mitigation, it's important to point out that mitigation of black carbon and methane in particular also generate direct health co-benefits. So, thinking about the relationship between these short-lived species and CO2, stringent and continuous mitigation of the short-lived climate pollutants could potentially increase the allowable amount of CO2 emissions going into the atmosphere for avoiding warming beyond kind of any desired level. And also, reductions of these kind of short-lived emissions could be a significant contribution to staying at or below the 2C or some other temperature threshold of concern. Okay, second finding from this chapter. and this starts to get into the carbon budget area. So stabilizing global mean temperature to less than 2 degrees Celsius, which is 3.6 degrees Fahrenheit, requires substantial reductions in net CO2 emissions prior to 2040 and likely requires net emissions to become zero or negative later in the century. Cumulative CO2 emissions must stay below about 800 gigatons of carbon in order to provide a 2/3 likelihood of preventing 2C. And given estimated emissions that we've put into the atmosphere since 1870, no more than about 230 gigatons may be emitted in the future to remain under this temperature threshold. And now if we assume that emissions from here on out are equal to or greater than a scenario referred to as RCP 4.5, this cumulative carbon threshold would be exceeded in approximately 2 decades. So once again, let me kind of unpack this and provide some more supporting info. So, this gets to how do we estimate these so-called carbon budgets? Well, a robust feature of model climate change simulations is that there is a nearly linear relationship between cumulative CO2 emissions and global mean temperature increases, irrespective of the details and exact timing of an emissions pathway. And why linear? So it turns out as CO2 increases in the atmosphere, there's a diminishing radiative forcing from CO2 per unit mass, but that diminishing effect is compensated by another diminishing effect, the diminishing ability of the oceans to take up CO2 over time. So limiting and stabilizing warming to any level implies that there is a physical upper limit to the cumulative amount of CO2 that can be added to the atmosphere. So eventually stabilizing the global temperature requires CO2 emissions to approach zero. So for a 2C or any desired global mean warming goal, an estimated range of cumulative CO2 emissions from the current period onward can be calculated. But there's a lot of uncertainty. And the key sources of uncertainty for any compatible forward-looking CO2 budget associated with any given future warming objective include, one, the climate sensitivity, that is, for a certain amount of additional CO2, such as a doubling of CO2, how much warming do you get? How sensitive, how responsive is the global climate to an amount of additional CO2? Another source of uncertainty is the response of the carbon cycle, including feedbacks. For example, the potential for the release of CO2 and methane from permafrost thaw as those northern latitudes warm. Other sources of uncertainty, the amount of past CO2 emissions. We don't have perfect information about how much CO2 has been emitted into the atmosphere since pre-industrial times, and the influence of past and future non-CO2 species. I think we just showed previously that the non-CO2 species can have a large effect. So also increasing the probability that any given temperature goal will be reached implies tighter constraints on cumulative CO2 emissions, and relatedly, for any given cumulative CO2 budget, higher emissions in the near term must imply the need for steeper reductions in the long term, because again, the exact timing of the emissions matter less. What really matters is the total cumulative amount of CO2 going into the atmosphere. So in our chapter, we estimated, I'll hold you in suspense for a little bit. So in our chapter, we estimated illustrative dates when cumulative CO2 emissions would reach amounts commensurate with eventual warming of 2C and 1C above pre-industrial levels. And our starting point were numbers from IPCC, and then the rest of this is frankly simple arithmetic, and there's no fancy modeling here. So according to best estimates in the literature available to us in this report, including from IPCC's fifth assessment report, 1,000 gigatons of carbon is the total cumulative amount of CO2 that could be emitted, yet still provide a 2/3 likelihood of preventing 2C of global mean warming since pre-industrial times. The 2/3 likelihood, or the 66% chance, simply indicates the 66th percentile of an ensemble of modeling runs that were considered that then result in 2C of warming. That estimate, however, ignores the additional radiative forcing effects of the non-CO2 species. And so, considering both historic and projected non-CO2 effects of...
People think this, okay, never mind. Sorry.
Yeah, I'm getting to it. When you consider the non-CO2 effects, it reduces that 1,000 gigaton number estimate to 790 gigatons, which is what we used here. And between 1870 and 2015, human activities, primarily the burning of fossil fuels and deforestation, emitted about 560 gigatons in the form of CO2 into the atmosphere. So limiting the global average temperature increase to below 2C means, therefore, that approximately 230 gigatons more CO2 could be emitted globally. So to illustrate, if one assumes future global emissions follow a pathway consistent with the lower scenario, RCP 4.5, and these scenarios, by the way, were used throughout CSSR and also are being used in Volume 2 of the National Climate Assessment. So if you follow an RCP 4.5 pathway from here on out, this cumulative carbon threshold is exceeded by around 2037, while under a higher scenario, referred to as RCP 8.5, this occurs by around 2033. And then if we were to give ourselves kind of a lower probability of eventually limiting warming to 2C, say a 50% chance, or a 30% chance instead of the 66% chance, then this would imply a larger amount of allowable cumulative CO2, and therefore a longer time before we reach those cumulative carbon thresholds. And those are those other dates you see there. Now, to limit global average temperature increase to 1.5 C, which by the way equates to 2.7 degrees Fahrenheit, the estimated cumulative CO2 budget is about 590 gigatons of carbon. And this simply assumes linear scaling with the compatible 2C budget. So linearly scaled with the 790 number up there. Now, if 590 is the total cumulative allowable amount, and then given what's been emitted since 1870, that is the 230 gigatons of carbon, then that would mean only about 30 gigatons more CO2 could be emitted, and a further emissions of 30 gigatons of carbon in the form of CO2 are projected to occur in the next few years. So, However, some caveats. Now, since our CSSR report, there is now more literature, actually a flurry of new literature, each doing their own estimate about the remaining carbon budgets for 2C and 1.5C. And many of these newer studies suggest that the world could emit more CO2 than we estimated in CSSR, yet still limit warming to 2C or even 1.5 thresholds. Many of these new studies have been done in response to the forthcoming IPCC special report on pathways to meet 1.5C, which, by the way, is scheduled to be finalized this October. So there has been a flurry of publications to make sure that individual papers would then get picked up by this IPCC special report. So this graphic here is not in our CSSR report. I borrowed this from a recent analysis that provided a really nice overview and analysis of all of these different recent studies. I'm not prepared to talk about each and every one of these, but I'd like to use this to illustrate a number of points. First is that there's a large range because different assumptions and different methods have a large impact on the estimate of the remaining carbon budget. So I mentioned some of these reasons previously. For example, what is each study assuming about past CO2 emissions? Are the studies using the same definition of, quote, pre-industrial to present? What are studies assuming about past and future non-CO2 effects? And what are studies assuming about climate sensitivity, i.e. the amount of warming response for a doubling of CO2? And there are differences in modeling approaches too. Integrated assessment models, which use simplified carbon cycle models, tend to employ kind of an optimized emissions pathway to achieve a targeted warming level by 2100. And sometimes you have an overshoot in that warming before coming back down to the targeted warming level in 2100. And then there are more complex Earth system models, and they tend to allow emissions to increase until that warming target is achieved, and then assume an immediate kind of cessation of emissions thereafter. Now, for 1.5C especially, because we're not that far away from that level of warming, estimates of remaining carbon budgets are very sensitive to these different assumptions and methods. Another factor here to consider is, again, how might positive feedbacks in the climate system, again, I'll refer to potential for CO2 and methane release from permafrost thaw, how might they further compromise and constrain allowable anthropogenic emissions to stay within certain warming levels? I do kind of hope that the forthcoming IPCC special report will help clarify the reasons for the differences among these estimates about remaining budgets for 1.5C and 2C of warming. But nevertheless, I think one of the main messages and bottom lines is that despite the range of estimates, I think the point remains that the scale of emission reductions necessary to get on the pathway to 2C is tremendous and perhaps unprecedented. Let me turn now to the 2-degree objective in a little bit more focus. So because this is often at the forefront of discussions, I wanted to provide just really brief background on it. The idea of a 2C goal can actually be found in the literature as early as 1975. So it's really not just because of the Paris Agreement that we talk about the 2C objective. Back in 1975, Nordhaus justified it by simply stating, quote, if there were global temperatures more than 2 or 3C above current average temperature, this would take the climate outside the range of observations which have been made over the last several 100,000 years. And so, since that time, obviously, this has gained attention in both scientific and policy discourse. Later, And this is a super abbreviated list. There are many other kind of milestones along the way. I'm providing really some very select highlights. Later, the Stockholm Environment Institute published a report in 1990 stating that 2C, quote, can be viewed as an upper limit beyond which the risks of grave damage to ecosystems and of nonlinear responses are expected to increase rapidly. Fast forward, 2007, the IPCC Fourth Assessment Report stated, among many other things, that, quote, confidence has increased that a 1 to 2C increase in global mean temperature above 1990 levels, that would be 1.5 to 2.5 above pre-industrial levels, poses significant risks to many unique and threatened systems, including many biodiversity hotspots. And now, most recently, of course, the Paris Agreement of 2015 took on the long-term goal of, quote, holding the increase in the global average temperature to well below 2C above pre-industrial levels and pursuing efforts to limit the temperature increase to 1.5 above pre-industrial levels. So essentially an objective stated as a global mean warming target serves as a proxy for the kind of environmental and societal risks that are of most concern. And there are some important considerations when using a global mean temperature objective as a proxy. One is that it's important to point out that global mean warming of 2C or any level does not mean, of course, warming of 2C everywhere. We know, for example, that the Arctic has been warming at about twice the rate as the global average, and we expect in the future that high northern latitudes will continue to show the greatest rates of warming, and in general, land masses warm more than the oceans. Secondly, the 2C or any global warming objective cannot be viewed as a bright line threshold. So as a bright line threshold below which there is no risk, and above which suddenly multiple thresholds or tipping points are crossed. There is a spectrum. So there's a spectrum of various levels of risk, and depending on a region's or sector's or a population's vulnerability and adaptive capacity, impacts and risks manifest themselves differently across regions and sectors for current and future levels of warming and climate change. But all of that kind of really starts to get into what NCA 4 Volume 2 will be all about. Vulnerabilities, impacts, and risks by region, by sector. Okay. So our third finding, again, let me read this one. Achieving reductions before 2030, consistent with actions announced by governments in the lead up to Paris, would hold open the possibility of meeting the long-term temperature goal of 2C, whereas there would be virtually no chance if net emissions followed a pathway well above those implied by country announcements. Actions in the announcements are by themselves insufficient to meet the 2C goal, but the likelihood of achieving that goal would then depend strongly on what happens pathways after 2030. So, supporting that statement, in our report we highlighted this work by Fawcett et al. So this study takes into account what each individual country pledged in the lead up to the 2015 Paris Agreement. The obvious caveat here is that the U.S. has since announced its withdrawal from the Paris Agreement. So this analysis still does include the U.S. non-binding pledge that was provided in the lead up to the Paris Agreement. So under a scenario in which countries maintain the same pace of decarbonization past 2030, as they announced in their first actions leading up to 2025 or 2030 in their INDCs, to use the Paris Agreement lingo. Let me point out, I'm talking about this relatively flat line in the middle of this graphic. So if you assume a consistent pace of decarbonization past 2030, as countries announced in their pledges, there is some likelihood, less than 10%, of preventing a global mean surface temperature change of 2°C relative to pre-industrial levels. So again, this scenario thus holds open the possibility of achieving this goal, whereas, again, there would be virtually no chance if emissions climbed to levels well above those implied by country announcements, so those higher trajectories that you see on the graph. So even greater emissions beyond 2030, based on assumptions of even higher decarbonization rates past 2030, would then increase the likelihood of limiting warming to 2°C, or even lower, increase the probability to about 30%. And importantly, a pathway like that would almost eliminate the likelihood of a very strong warming, would almost eliminate the likelihood of a global mean temperature increase of around 4°C or greater, which would equate to around 7 degrees Fahrenheit. And then scenarios that would assume even greater emissions past 2030 would be necessary to have at least a 50% probability of limiting warming to 2°C. So I'll start wrapping up by I want to end with this final finding from our chapter. So there is increased interest by some scientists and policymakers in exploring additional measures designed to reduce net radiative forcing through other as yet untested actions, which are referred to as geoengineering or climate intervention actions. So these climate intervention approaches are generally divided into two categories. There is carbon dioxide removal, or CDR, and there's solar radiation management, or SRM. So both of these methods would reduce global average temperature by reducing net global radiative forcing, CDR through reducing atmospheric CO2 concentrations, and SRM through increasing Earth's albedo, or reflectivity. The last strategic plan of the U.S. Global Change Research Program, USGCRP, did call for the beginning of, I would say, a modest effort to do some research in this area. But I do think the challenges of limiting warming to 2°C do invite questions about this topic, but still, we absolutely recognize that this is a sensitive and controversial topic. Our statement in the CSSR report is what our kind of bottom line statement on this topic in the CSSR report is what you see here. Further assessments of the technical feasibilities, costs, risks, co-benefits, and governance challenges of climate intervention or geoengineering strategies, which are as yet unproven at scale, are a necessary step before judgments about the benefits and risks of these approaches can be made with high confidence. So greenhouse gas forcing has the potential to push the climate farther into unprecedented states and increase the likelihood of, quote, surprises. And in fact, I would refer you all to chapter 15 in the CSSR report, and I believe the last seminar series was on that topic, which addresses this issue of the potential for surprises as you push the climate. And proponents, or if that's the right word, of some of these climate intervention strategies put forward that to prevent climate change from reaching a state with more unpredictable consequences, climate intervention could potentially help reduce that. So I'll just say a few more things about this in general terms. So in principle, at large scale, carbon dioxide removal could reduce CO2 concentrations, that is, in theory, cause net negative emissions. But to realize sustained climate benefits from carbon dioxide removal, the removal of CO2 from the atmosphere would essentially have to be permanent, at least several centuries or millennia. In addition to what might be high cost, CDR might have the additional limitation of long implementation times. Also, scenarios in which large-scale carbon dioxide removal is used to meet a 2C limit while allowing business as usual consumption of fossil fuels is probably not feasible with current technologies that exist today. By contrast, solar radiation management offers an identifiable intervention method of cooling Earth within a few years after inception. An important limitation of SRM, however, is that it would not address damage to ocean ecosystems from increasing ocean acidification due to continued CO2 uptake. And SRM could theoretically have a significant global impact even if implemented by a small number of nations, and including by nations who themselves are not also major emitters of greenhouse gases. Some other points for solar radiation management actions, even if the reduction in global average radiative forcing from SRM were to be exactly equal to the positive radiative forcing from greenhouse gases, the regional and temporal patterns of these forcings would have important differences to consider for the climate. And while SRM could, in theory, rapidly lower global mean temperatures, the effects on precipitation patterns, light availability, crop yields, acid rain, pollution levels, temperature gradients, and atmospheric circulation in response to these kind of things are currently obviously less well understood. So there are a lot of important dimensions to this topic that do go beyond scientific and technical considerations, and those were well beyond the scope of our CSSR report. But those are, among those are the potential development of global and national governance and oversight procedures. There are geopolitical considerations, legal considerations, environmental, economic, societal impacts, ethical, generational considerations, and in relationship to current climate and greenhouse gas mitigation and adaptation strategies and policy. So it is clear that these social science and other non-physical science dimensions are likely to be a major part of the decision framework and ultimately control the adoption or the non-adoption of these kind of climate intervention approaches. So I'll end there. The link here is the direct link to the chapter that this presentation is based on, and thanks for listening.
Thank you, Ben. We already have a question online. First of all, I want to tell the folks online, I'm sorry I can't enlarge the screen. I'm relatively new to Adobe Connect. I will look into it. It looks like some people were able to have a larger screen and others weren't, but I'll look into it. So Angela Anderson has a question. Can you talk more about what emissions trajectory is required post-2030 to increase likelihood of staying well below 2 degrees C for the lowest line in your slide where you showed that slide? I think it was about 3 or 4 slides back.
Sure. Well, one part of the answer is that there is no one single pathway that would get you there. There would be multiple ways in which those emissions could decline. Steeper versus more gradual. But generally, the one scenario used in the IPCC reports, the RCP 2.6. That's the lowest scenario considered in the IPCC reports, and that scenario has the greatest chance of being consistent with the goal of 2C, but I think the forthcoming IPCC report will show that you need to consider scenarios, in some cases scenarios that even go below the RCP 2.6.
Okay, thank you. And Christy Dahl has a question. Given the long residence time of CO2 in the atmosphere, can you talk about warming beyond 2100?
Sure. So, like I said, the CO2, at least a fraction of the CO2 that we emit now, is going to stick around for a really long time, past 2100. Unless, of course, we are successful down the road with carbon dioxide removal technologies that could, suck CO2 back out of the atmosphere. But in the absence of that, we are committing ourselves to long-term warming past 2100. And it's true that a lot of the scenarios that you see on the graph kind of stop at 2100, but that does not mean that warming stops at 2100. In fact, in the last IPCC report, they did consider a few scenarios that went out to 2300. And it does show that for those scenarios that don't bring CO2 down in a hurry within this century, that you do have continued warming. And in fact, the other component of the climate system that's really important to think about past 2100 is sea level rise. There's someone in the room here who knows a lot more about this than I do, but there's so much thermal inertia that gets built into the oceans that even if you stabilize CO2 concentrations, the amount of heat that goes into the oceans essentially commits us to long-term sea level rise well past 2100.
Okay, thank you. And then we have another question. Kurt asks, any thoughts on offsetting our carbon footprint by planting trees?
Well, sure. Planting trees is a good thing. It's good for a number of things, and there can be urban heat island benefits as well to planting a lot of trees in urban areas. The carbon stored in those trees needs to stick around and remain secure for a long time to get the benefit. But it's going to take more than a few of us planting some additional trees to really bring down the trajectories of CO2.
Okay, and then thank you. And then Paolo Delgado asks, how are models taking into consideration the use of biomass and biofuels? Do they consider them carbon neutral?
Oh, this is a really good question. It's getting out of my area of expertise, but I do know that the assumptions in the models that look at really stringent emission pathways that try to get us to a 2C or 1.5 do include a lot of assumptions about biomass fueled power plants with carbon capture and sequestration. So if you're burning the biomass, the assumption is that you might still have carbon capture technologies in order to go along with that, in order to try to produce these negative emission scenarios that you do see in the modeling that try to get us to a really low temperature threshold. You do see negative emissions by the end of the century, and that underlying that is our assumptions, strong assumptions about the use of biomass burning with carbon capture and storage.
Okay, and then Marcy Rockman asks, really glad you mentioned the roles that social science and ethics, for example, should or will play in working through geoengineering issues. Are you aware of major efforts to gather or foster such social science work and discussions?
If the question is about the climate intervention and geoengineering issues, yes, there are forums. There are forums out there, and folks are talking about this. I don't want to speak out of hand. I'm aware of some. I don't have the exact names of them in my head right now. But the short answer is yes. There are some forums out there talking about the social and governance dimensions.
Okay. And Colin asks, what is the median amount of CO2 removal needed by 2100 in order to have a 66% chance of staying within a 2 degrees C temperature rise? How quickly do these scenarios suggest CO2 removal will be needed?
Yeah, it is. It's again. There's a range of answers, because there are, again, there's no single pathway to provide a 2/3 likelihood. There are a range of pathways, and I hope my presentation didn't imply that it's only scenario A, B, or C. There are multiple pathways. But what we did show in our chapter is that scenario of the 60% likelihood is indicative of the total amount of cumulative carbon that would have to go into the atmosphere, and then depending on how much CO2 removal is necessary, well, that would depend on how you get there in the first place. There's the short answer is there's a range. If you continue to assume strong use of fossil fuels and not much renewable, then you will need a lot of CO2 removal. If you assume a lot of renewables to get you there, then you will not need to rely on CO2 removal as much. I don't have a quantitative answer.
Christy says, thank you for your earlier response. And Dennis Miller asks, solar panel production and wind farms are coming online at an increasing pace. Without government action, do you see market forces as being strong enough to make a difference in keeping global warming down somewhat?
The trend is towards the costs for these technologies are coming down, but again, this is kind of an area that's a little beyond my scope. So I unfortunately have to kind of punt a little on that one.
Okay. And then Annie Armstrong asks, Adam Corner has published several papers on attitudes towards geoengineering. I'm not familiar with those. Are you? I'll have to check them out. Thank you, Annie. I have one question, Ben. So are we already at 1 degree? Have we already increased 1 degree? I thought I remember Catherine Hayhoe saying that.
We are about there.
And where was the baseline for that? Do you remember what year? Is it like 1990, 1900? I can't remember.
The baseline for that should be like late 1800s to early 1900s.
So we've already gone 1 degree. So are we talking basically 1 more degree? I'm not sure the baseline. I kind of don't know where we are relative to when everybody talks about 2 more degrees. If we're already at 1 degree, does that mean we have 1 more degree to go till we get to 2 degrees C? You see what I'm confused?
Yeah. I mean, that's basically right.
Okay.
The other thing is that we would, we would need, you would also need a number of years to be able to confidently say that, we are, quote, now at 1.5 or 2, because, the average global temperature obviously still fluctuates. There is a growing trend. It would be some time before you could confidently say that you were there. Again, these are kind of proxy metrics. They're not kind of magic bright lines that you suddenly trigger into.
But if we are at about 1 degree C over already, it kind of gives me a sense of more immediacy, like we're frogs in the pot, It's a little bit like, uh-oh. Anyway, sorry, just, any other questions?
Frogs in the pot.
Yeah, they're boiling, almost boiling. Lindsay asks, not much attention has been paid to ozone as a climate forcer. Can you talk a bit more about that?
So in the graphic I showed from the report, ozone is included in there. So it absolutely is part of the radiative forcing estimates, and it's also been the precursors of ozone, including the connection with methane, have been discussed as mitigation strategy that could get you both near-term climate benefits, but also provide strong health co-benefits.
Okay. Are there any more questions? Well, Ben, thank you so much for presenting. That was great. And I just want to tell you, next week we have August 16th, The Causes and Consequences of a Rapidly Changing Arctic by Patrick C. Taylor, climate research scientist at NASA. So we hope you can join us next Thursday for that. Thanks again, Ben.
Thank you.
And folks online, if you're interested in getting a recording, you can get a recording and a PDF. For those of you who had problems seeing the screen today, you can, Ben has provided a complete PDF, and that will be on the same site that Katie noticed in the chat. Katie, any last words? And Ben, any last? Oh, go ahead.
Nope, nothing for me. Thanks so much for joining, and I just dropped the link back in the chat box.
Thank you, Katie.
Sorry.
Ben, thanks again.
Thank you.
All right, everybody, bye-bye. Thanks for joining us.
I got a meeting.